Okay, in this video, I'm going to show you the mechanism of acidic hydrolysis. And so this is just going to be, you can do this with any carboxylic acid group. I'm going to show it with an ester, and I'm just going to show the reverse of the Fischer esterification we did in the last video. But this mechanism will work for acid chlorides, anhydrides, thioesters, esters, amides, nitriles, whatever. And so the key here, the way we drive this reaction to the right is by choice of solvent. So we add acid, and the acid can be a catalyst, right? This can be catalytic, which starts with a C. And then the water is the nucleophile. So again, let's look at this. As I showed in the Fischer esterification video, you always want to protonate the oxygen. And you can see this because the sp3 oxygen here is pushing electrons up at the carbonyl. I'm going to draw this resonance structure like this. You don't have to, right? This has a resonance structure that looks like that. Right, so two resonance structures there. The charge is distributed over these two oxygens. So always use the carbonyl oxygen to grab the proton. That oxygen, the double bonded oxygen, is the one that's going to get the proton. Now, once you've done this, this is now a powerful electrophile. Water can add in. So remember, water adds in, so not OH. We're under acidic conditions. There's nothing to pull the proton off water, and we can't have strong base in acid. Okay, and now again, like in the last slide, this is going to be a solvent-assisted proton transfer. The oxygen, this oxygen can't get in here where it needs to. So really, the basic atom here, right, the basic atom has got to be lined up with the O and the H. So there's an H. What am I doing? I'm going to put this H up there. Lone pair, and then an H there. Right, and this is how the solvent-assisted proton transfer works. The oxygen here grabs that the acidic hydrogen. This is an equilibrium. Neutralize that, but then sitting right there is the ethyl. Remember, we want to break the ethoxy off, and so the proton is there. So water doesn't really have to move at all. If it just comes in here and collides with these two, this OH can be used to transfer the proton. Doesn't have to be the same proton. Okay, now we get so now we have a protonated ethanol. Ethanol leaves or is pushed out by an ethoxy. And that gets us our ethanol. So there, we've made our ethanol. That's one of the byproducts. So in acidic hydrolysis, the leaving group's going to leave and be protonated. Okay? And now we've got a protonated carboxylic acid. Water will come and take this proton. We regenerate our catalyst, and we get our equilibrium. Okay, so again, this is just the reverse of the Fischer esterification. The Fischer esterification only works to make esters. All right, in the last video, Fischer esterification only makes ester, hence the name esterification. Acidic hydrolysis will work with any of the carboxylic acid derivatives, including amides. All right, so this is a mechanism you need to have worked out. Oh, and I guess the other thing is, if you don't want to draw all this out, once you understand this, you can just do that, and you can write SAPT, solvent-assisted proton transfer.